Imagine you have a paint gun. You aim it at a wall through two narrow slits in a metal sheet. You fire thousands of tiny paint pellets. And on the wall behind, you see exactly what you'd expect. Two vertical stripes, one behind each slit. Now replace the paint gun with a beam of light. Fire it through the same two slits. And on the wall behind, you don't get two stripes. You get dozens. Bright bands alternating with darkness. A pattern that shouldn't exist if light were just tiny pellets. This is the double-slit experiment, and it's about to get much stranger. In 1801, a British polymath named Thomas Young stood before the Royal Society in London with a radical claim. Light, he said, is a wave. At the time, this was dangerous. Isaac Newton, the most revered scientist in history, had declared light to be a stream of particles. His corpuscular theory had dominated physics for over a century. Textbooks taught it. Professors defended it. No one dared challenge it. Young was 28 years old. He'd already learned 14 languages, helped decipher the Rosetta Stone, and earned a medical degree. But none of that mattered. Challenging Newton was academic suicide. He did it anyway because he had evidence. He designed an elegantly simple experiment. Sunlight passes through a tiny pinhole, creating a single, coherent source. That light then hits a card with two thin slits cut into it. Behind the card, a screen. If light were particles, you'd see two bright bands, one behind each slit. Simple geometry. But Young saw something else entirely. Alternating bands of light and dark, bright where wave crests from both slits arrived together, constructive interference, dark where a crest met a trough, destructive interference. The pattern was unmistakable. Light behaves as a wave. Waves from the two slits overlap, reinforce and cancel. The bright bands aren't random, their spacing depends on the wavelength and the distance between the slits. Young had overturned Newton, and for a century the case was closed. Light is a wave. Until it wasn't. In 1905, Albert Einstein showed that light comes in discrete packets, quanta, which we now call photons. Each photon carries a specific amount of energy. Light is not a continuous wave, it's made of particles. But wait, if light is particles, what happens when you send them through two slits one at a time? This is the question that haunted physicists for decades. And in 1989, Akira Tonomura and his team at Hitachi in Japan answered it. Not with photons, but with electrons. They built an electron source so faint that only one electron existed in the apparatus at any given moment. One electron. Alone. No other electron to interfere with. They fired electrons one by one. Each electron hit the detector screen as a single dot. A particle. Exactly what you'd expect. After 10 electrons, just random dots, no pattern. After 100, still random. You'd think you were watching raindrops hitting a window. After 1,000, something begins to emerge. A faint structure in the noise. After 10,000 electrons, each traveling alone, each hitting the screen as a single point. An interference pattern. The same pattern Young saw with his beam of light in 1801, bright bands and dark bands. Constructive and destructive interference, as if each electron were a wave, passing through both slits, interfering with itself, and then arriving as a particle at one specific point on the screen. But interference requires waves overlapping, and there was only one electron at a time. Nothing to interfere with, unless each electron somehow passes through both slits simultaneously. Unless each particle interferes with itself. In 2002, readers of Physics World voted this the most beautiful experiment in all of physics. Here's where reality breaks. You might think, fine, the electron goes through both slits. Let's just watch it. Let's put a detector at one of the slits to see which path the electron actually takes. So physicists did exactly that. They placed a detector near one slit, a device that could register whether an electron passed through it. A simple measurement, just looking, and the interference pattern vanished, gone, completely. Instead of the beautiful wave-like bands, the screen showed exactly two clumps, one behind each slit. As if the electrons had suddenly remembered they were particles. The moment you gain information about which slit the electron went through, it stops behaving like a wave. It behaves like a particle. Two bands. No interference. Turn the detector off. Don't look. And the pattern returns. Every time. Turn the detector off. Don't look. And the pattern returns. Every time. This isn't about the detector physically disturbing the electron. Physicists have designed increasingly gentle measurements, using single photons to tag the electron's path without significantly altering its momentum. The result is always the same. It's not about disturbance, it's about information. If which path information exists anywhere in the universe, even if no human looks at it, the interference pattern disappears. The electron seems to know whether its path can, in principle, be determined. Richard Feynman called this the only mystery of quantum mechanics. Not one mystery among many, the only one. Every other quantum puzzle, he argued, is just this same mystery wearing a different costume. In 1978, the physicist John Archibald Wheeler pushed this mystery to its logical extreme. He proposed a thought experiment. What if you wait until after the particle has already passed through the slits, and only then decide whether to measure which path it took? Think about what this means. The electron has already traveled through the apparatus. It has already decided to go through one slit or both, and yet your future choice of measurement seems to determine what it did in the past. Wheeler imagined this on a cosmic scale. Light from a distant quasar, billions of light years away, bent around a galaxy by gravitational lensing, taking two paths around the galaxy. A cosmic double slit. The photon left the quasar billions of years ago, and yet your choice of detector today, whether to measure which path or to look for interference, seems to determine how that photon traveled billions of years in the past. In 2007, a team in France performed Wheeler's experiment in the lab. They confirmed it. The delayed choice works exactly as quantum mechanics predicts, and it gets stranger still. In 1999, Yoon Ho Kim and colleagues performed the delayed choice quantum eraser experiment. They created pairs of entangled photons. One photon goes through the double slit, the other, the idler, goes to a separate detector. If the idler is measured in a way that reveals which path information, the interference pattern for its partner disappears. If the idler is measured in a way that erases the which path information, the interference pattern returns. The choice of how to measure the idler can be made after the signal photon has already hit the screen. The past, it seems, is not fixed until the future decides how to look at it. The universe doesn't seem to care about the order of events. It cares about whether information exists. After a century of debate, physicists still disagree about what the double-slit experiment tells us about reality. Three major interpretations compete. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, says, "Don't ask, what the electron is doing when you're not looking? The question has no meaning. Quantum mechanics doesn't describe reality. It describes what we can observe. The wave function isn't a physical wave. It's a mathematical tool for calculating probabilities. When you measure, the wave function collapses to a definite outcome. The many-worlds interpretation proposed by Hugh Everett in 1957 says, the electron really does go through both slits, and when you measure it, the universe splits. In one branch, the electron went left. In another, it went right. Both outcomes are real. Both versions of you exist. There is no collapse, only branching. The pilot wave theory, first proposed by Louis de Broglie in 1927 and revived by David Bohm in 1952, says, the electron is always a particle. It always goes through one slit. But it's guided by a real physical wave, a pilot wave that goes through both slits and creates the interference pattern. The wave is real. The particle surfs it. Each interpretation makes the same predictions. No experiment has ever distinguished between them. The math works. The mystery remains. And that might be the strangest thing of all. We have a theory that predicts the outcome of every experiment with extraordinary precision. We can calculate exactly where the bright bands will appear, exactly how wide they'll be, exactly how the pattern changes when we adjust the slits. The math is perfect, but we cannot agree on what it means. Richard Feynman once said that the double-slit experiment contains the heart of quantum mechanics. In reality, he said, it contains the only mystery. 2 slits, 1 particle, and a pattern that shouldn't exist. We can predict it, we can use it, we can build extraordinary technologies on it. But after more than a century, we still can't explain why.